In this video, I'm going to be going over how to do some of our calculations for the two equations we have when it applies to a heating or cooling curve. First thing to note is that we have a heating and a cooling curve that are the same thing, just the reverse of each other. So segment 5 is considered a gas for both. It's just whether you're starting or ending with it. Same thing with segment 1 being a solid, just determining where you're starting or ending. Knowing kind of what segment will help as we are labeling the equations we have. So if you look at the next page, you'll see there are a lot of constants that go with a heating curve. And depending on what our problem is asking, we need to make sure we're using the right one. So first, before we get into doing a sample problem, we're going to organize which constant goes with what segment. And also, if you notice, there's two equations. We're going to organize what equation is going to go with what segment. So going back, we should see that there's kind of two types of things happening. There's the things that are happening in segment 1, segment 3, and segment 5, which is the kinetic energy increasing as the temperature and speed increases or decreases, depending on if you're heating or cooling. And then there's the phase changes that are happening in segment 2 and in segment 4. Based on this, we should be able to determine that if we look back at our equations, we have this equation where it's Q equals mc delta T. The other equation, if we look at it, is Q equals HM. Because segment 1, 3, and 5 are dealing with temperature changes, it makes sense that the temperature change is included in that equation. It would not make sense to have a temperature change included in QHM because the temperature change would be 0, and anything times 0 would be 0. And we know that either heat is being absorbed or released during those phase changes. So having a temperature change of 0 would nullify any other numbers and not give us an accurate result. The next step then is figuring out what constant goes with what segment. Because segment 1 represents solid state for the heating and cooling curve of water, that constant is 2.11 joules per gram degree Celsius. What that means is that it would take 2.11 joules to raise 1 gram of solid water 1 degree Celsius. Next, we have water, liquid water specifically, which is 4.18 joules per gram degree Celsius. So similarly, that's going to mean if I want to raise the temperature of liquid water 1 degree Celsius, 1 gram of it, I would need to put in 4.18 joules. And then lastly, we have gaseous water, 2.00 joules per gram degree Celsius. Next, we have our other constants, which are heats of, which is represented by the letter H. So heats of are going to be 334 for fusion. Fusion is freezing / melting, less obviously named than the other one. But when we're talking about the heat of fusion, that's melting or freezing. The unit here is just joules per gram, which should make sense because temperature is not involved. So it's just how much energy you need to put in to either, well, in this case, melt or freeze, get energy in or out for 1 gram. And then the last number is 2,260 joules per gram. And again, these numbers are coming from this kind of energy constants. So looking at all of these numbers, you can clearly see in segment 4, which should be the heat of vaporization, that value is a lot higher than melting. And that makes sense. As we have discussed, trying to vaporize something completely requires a lot more energy because you need to completely sever attractive forces between other molecules, comparing only to weakening in segment 2. Now it'll be time to start some example problems. In number 1, we have a cup of coffee cooling from 75 down to a comfortable room temperature of 20 degrees. How much energy does it take to release to the surroundings? So the answer is in parentheses here, but we'll go through how that answer has come to be. For these problems, I want you to draw out a heating curve or a cooling curve. So in this case, because of the word cool, I know that it should be a cooling curve. So I'm going to kind of trace that out here. And then I can decide that cooling curves should be exothermic. They should be releasing energy, which is going to result in a negative answer. So if you determine that you have an exothermic situation, it should always end up with negative heat because you're releasing heat to the surroundings. The next step in this problem is to decide where I am on the cooling curve. What segment am I in, or segments am I in? And so the first number given to us is 75 degrees, which would be contained for water, which we're going to assume, in segment 3, because I know that melting happens at 0 and boiling happens at 100. So 75 is between those numbers, and so is 20. I'm only in segment 3 then, so that is one equation I'll need to do. Segment 3 is going to use the equation Q equals mc delta T, commonly referred to as MCAT. And I can plug in all my numbers. For a lot of these, we're just going to be kind of plug and chugging, not necessarily rearranging. There are some that you will need to solve for other things, but for a lot of these, we're just looking for total energy in or out. The mass in this problem was 140 grams. The specific heat of liquid water, if we recall, is 4.18 joules per gram degree Celsius. And lastly, we have a temperature change of 20 degrees for our final temperature from 75. You always want to do final minus initial here, and then this is degrees Celsius as well. One thing that will work out with your units is that the units should cancel for whatever you're solving for. And then that Celsius would just be 1. So I will have joules end up being my unit. Now when I calculate this, I'm going to get an answer of 32,186 joules. Based on the numbers in the problem, I'm going to round that so it's only one sig fig. Sorry, this should be a negative because that temperature would be negative. 32,000 joules, negative 32,000 joules would be how much energy is released in that example. Most of the problems will be dealing with water. However, if there is a problem that doesn't involve water, just try your best to figure out what the problem is asking and kind of decide if you are involved in more than 2 segments or more than 1 segment, what numbers you would need for those. Because obviously the specific heats, if you don't have water, are not going to be 4.18 or 2.11 or 2. The next example problem is going to have more than 2 segments involved. So I'm just going to go through one more example with that and then let you kind of try the other ones on the worksheet yourself. So in this problem, same thing as before, we want to decide, is this heating or is this cooling? An ice cube tray full of ice at -7 is allowed to warm up to room temperature. How much energy must be absorbed by the contents of the tray in order for this to happen? So that means this is heating. And that also means it's going to be endothermic. Now, thinking about the temperatures it gives me, I have -7, which would be in my solid segment, because I know that ice melts and freezes at 0. And then I have 22, which is going to be in my liquid segment, which means I'm going through 3 different segments. And if you recall, every segment has its own value associated with it. So that means, if we recall again, that we melt and freeze at 0, I have a temperature change going up from -7 to 0. And then at 0, I completely melt. Then, once I'm done melting, I'm still at 0, but now I go up to 22. So I need to calculate every segment separately in order to get the correct answer. For my slanted, my segment 1 and 3, I'm going to be using Q MCAT, or Q equals MC delta T. And these will not be set up exactly the same way because of the fact that they do have different temperature changes, and also that they have different specific heats for solid and for liquid water. The mass, however, is going to be the same, so 235 times specific heat of solid water, which is 2.11, then times the temperature change here, which is going to be 0 minus -7, which will give us +7. For this third segment, similarly, I'll have 235 for my mass. And then I'll have liquid water specific heat, which is 4.18. And then this temperature change is going to be 22 minus 0, which is just +22. And then this equation will be slightly different because it is melting. So we have our QHM here. H is going to be the heat of fusion, which is 334 joules per gram. And then the mass is still going to be 235. And kind of like before, you see that the unit should cancel, so only joules is left in all of these. So quickly, we'll go through and get our answers for this. For all of these, we should get positive values. One quick thing to note is if it were a cooling curve, our Q MCATs, because of our temperature, would come out negative. However, our phase changes, we need to provide the negative in there because they would be cooling. And so just be forewarned if you have a problem like this, but it's cooling curve instead, and you get a negative answer for segment 1 and a negative answer for segment 3, your answer for segment 2 should also be negative. It just is that maybe you forgot to put the negative sign with it. Then once you get them all, you're going to add them together. And you're going to want to round that to sig figs. If you look in our problem, all of our answers have 1 sig fig. So, or sorry, 3 sig figs. So that is where that number is coming from in parentheses. And this is just a quick little run through of kind of how to do these problems.